In this video, we're going to start looking at continuous distributions, so distributions of random variables that are continuously distributed instead of discrete distributions. The binomial distribution and Poisson distribution, those were discrete distributions. But something like a standard normal distribution, that would be a continuous distribution. And so what is a standard normal distribution? Well, a standard normal distribution, it has a density graph, and we'll talk more about density graphs here in a minute, but it has a density graph that satisfies the following. It should be bell-shaped, so it's bell-shaped, and it is symmetric about the mean. So it's bell-shaped, and it is symmetric with a mean of 0 and a standard deviation of 1. So we have our mean here. That is like this middle area, and the standard deviation for a standard normal distribution, that standard deviation is 1. So that's what we have. So let's take a look at some things. To represent probabilities associated with continuous random variables, we use density curves instead of a probability distribution. And so these are going to be different than what we use for discrete random variables. The major difference is going to be this. The probabilities for continuous random variables, we find those by finding areas under curves, right? So the area under a curve, under one of these density curves, it is the probability associated with that. Right? And so we'll look at this a little bit more again. But let's think about what we know about probabilities. If we were to add up all of the probabilities of everything that could possibly happen, you add all that up, that should add up to 1. And so the total area under the curve, under a density curve, it must equal 1. Right? So that's one thing that must happen. The second thing that has to happen is the height of the density curve must be non-negative. And that sounds like a strange way to say that it should be positive. Well, it's not a strange way to say it's positive because it means it's positive or it could be 0. So all that's telling us is that the height of the curve, we couldn't have a density curve that goes below the y-axis. Right? So I'm going to draw just some random axis here. You could possibly have a density curve that does this. So I don't know how well you can see this. Let me make that up. So you could have nothing for a long time, and then it could go up, and then back down, and then nothing for everything else. Right? So as long as the area under this curve, as long as all of that area was equal to 1, this would be a density curve. It would describe some kind of distribution. And so if we wanted to find, so maybe this value right here is 1, and this value up here is 3. And so the area, total area between 1 and 3 is equal to 1. If we wanted to know what's the probability that it is between 1 and 2, we can look at the area under just that part that is between 1 and 2. So that's how we deal with density curves. We look at areas under these curves. Sometimes those curves are just like straight lines. Other times they are curved like a normal distribution, right? So you have this bell-shaped distribution. So we'll take a look at both of these. Next time we are going to look at a particular kind of density curve that is called a uniform distribution. All right, we'll talk to you then.